work done with the negative sign. Why? Because the direction of the conduction current is different as the induced current. Conduction current is that current which is flow from the battery to the conductor. An induced current is the one which induces, or you can say temporarily produced in the conductor by changing the magnetic field. Alright,
Okay.
so long story short, the magnetic energy is represented by U, and it will be equals to half of Li square. This is the formula for magnetic energy. Now, what L is? L is inductance. L is self-inductance, or you can call it inductance as well. And I is current. I is
Current.
alright.
Okay.
Now, if you put the value of L over here, this is the value of L. If you put over here, you get the answer just like that, half mu naught n square E over L into I square. But you have to remember this formula, because most of the questions will be asked according to this formula. Alright?
Okay.
Okay.
So what can you explain? Okay, so L is the current, right? I mean the self-inductance.
I is the current and L is the self-inductance.
Okay.
Okay. And this L is the length of the. This L is the length of the inductor. Okay.
Okay.
Now let's talk about the transformers. Transformer is a very important topic. Let me just solve it for you here. Transformer, or you can say PMT, pole mounted transformer. So, what transformer is? First of all, let's such a device which is used to alter the current or potential difference. Potential difference means the voltage. Alright.
Okay.
This transformer So this is what we call a transformer. Transformer is a device which is used to alter the current or potential difference. Why do we need to alter the potential and the current? Actually, the electricity is produced by the grid station, and from the grid station to our houses there are plenty of a distance, and we know that the larger the distance we have, the more losses we'll have to bear. The loss of electricity is way too high as the as the distance increases. So in that case, Vera, we in our houses in Pakistan we need 220 volt in every socket in any switch of our house, and in America you need 110 voltage, right?
Right.
So, so we just need 110 volt, or you can say 220 volt. But if we talk about the voltage from the grid station to the PMT, or you can say transformer, the voltage is usually 900 volt or 11,000 volt. It is that huge voltage they provide. But uh, after the PMT alters the current and the voltage as well for our for our houses for our desired output, because we need only 110 volts, or you can say 220 volts. So the 11,000 volts converts into 220 volts. Obviously, there is a massive huge of energy loss by the transformer, but we need only 110 volts. So I don't care about the energy loss. I only care about the desired voltage at which our appliances, my home's appliances will work smoothly. So transformer. So why the grid station provides 11,000 or 1100 volts? Because there is a massive losses in between the grid station to the PMT. So if you provide, or you can say if the grid station provide only 110 volts after receiving or at the end of the PMT, we got nothing, or you can say we got only 10 to 12 volts. Why? Because all the voltage are lost in between the distance from the grid station to the PMT. So they provide extra voltage to compensate that loss. Okay?
Okay.
You get? Do you get it? Do you get it, Pira?
Yes.
This is what we call primary winding. Alright?
Okay.
And this is what we call secondary winding. At the secondary winding, we got the output, and at the primary winding, we have the input. This is input winding, this is output winding. Alright?
Okay.
Now this is a metallic loop, but the metallic loop is uh, what should I say? It is not directly connected with the secondary coil, because if the two coils are connected by the only metal uh, piece, their current will be shared and the circuit will be short circuited. So, in order to rectify this problem, they use few insulators along the path of these loops in order to get rid of the short circuit. So, what will happen in this device? The AC input, the AC supply or AC input is being transferred the AC signal is provided at the end of the primary winding. So when the AC wait, this is the AC signal. When the AC signal is provided at the input end, due to the change in current, or you can say due to the change in potential. Now, for suppose this is the current cycle. So current is changing continuously, Pira. At the very start, current is zero. This is the zero line. Alright?
Okay.
So at the very start, the current is zero. And after that, current is increasing. At this point, the current has its maximum value. And after that, the current starts decreasing and turns to zero. And after that, it increases in the opposite direction, and when it reaches the negative highest current, it will move up to zero. So current is continuously changing, and we know the relation between the current and the magnetic field. If the current changes, so as the magnetic field, right?
Right.
Now, Kira, what will happen if the magnetic field is changed? What will happen if the magnetic field is changed?
So does the current.
The current changes the magnetic field. But what about if the magnetic field is changed? What will happen in the primary coil and in the secondary coil as well?
Does the current stay the same then?
Yeah. According to Faraday's law, the magnetic field is changed. What will happen?
It's going to be a voltage.
Should I read this one? The Faraday law of electromagnetic induction. Read it.
Okay, so there's going to be an induced EMF produced. So when there's a change in the magnetic field, an EMF is produced.
The induced EMF is produced. So, in the primary coil, the current is continuously changing, and if the current is continuously changing, the magnetic field is changing as well. And according to the Faraday's law, according to the Faraday's law, the induced EMF is produced if okay.
Okay.
Now the induced EMF is produced if the change occurs in the magnetic field. Now we both agree with this point, right?
Right.
But in which coil the EMF is produced? The primary coil or the secondary coil?
Secondary.
Why not primary?
Because that's where the magnetic field is changing. And the output is in the secondary.
Does Faraday law restrict that if the change in magnetic flux in first coil, the induced EMF is always produced in the secondary coil? What if we have only one coil? Then why don't you read our last lecture? Why? These are the very difficult topics. If you're not going to reread or learn it before the class, you can't be able to get my lectures. You can't be able to understand it. So, Pira, we have discussed two things previously. First one is self-inductance, and the first one is mutual induction, and the second one is self-induction. Mutual induction tells us that if the induced EMF or if the change in current or change in magnetic field in one coil, the induced EMF produced in the secondary coil. And when I teach you that topic, I told you this, the induced EMF is produced in both coils below. In both coils, but in the mutual inductance, we are keen to read the induced EMF of the secondary coil, not the primary coil, because we have another topic which we call the self-inductance, in which we have to study the coil. We have to study the induced EMF within a coil at which the current is changing. So, whenever the current changes, the magnetic field changes, and due to the magnetic field, or you can say due to the change in magnetic flux in any of the coils, the induced EMF is produced in both the coils, in the primary coil and in the secondary coil as well. Now, are you getting my point, Pira?
Okay.
Okay. Now we conclude that if the magnetic field change occur in one coil, the induced EMF is produced in both the coils. We are agreed upon this. So, induced EMF is produced in both the coils. And in the primary coil pair, NP where this formula comes from, Pira? This formula comes from the Faraday's law of electromagnetic induction. Wait, let me show you. E is equals to negative n delta phi over delta t. So this formula comes from the Faraday's law of electromagnetic induction. Alright?
Okay.
Now, what is EP? EP is the induced EMF in the primary coil. What is the NP? NP is the number of turns in the primary coil. Alright?
Okay.
And this is the change in magnetic flux per unit. Now, let's talk about the other one. So now let's divide both the equations. Divide them. ES over EP is equals to negative NS delta phi B upon delta T and negative NP delta phi B over delta T. So negative cancels by negative delta phi B T. Delta phi B T cancels. So the formula we got is this: ES over EP is equals to NS over N. So it means that the potential which we got in the output is totally depends upon the number of turns. The number of turns of the coil. If you see closely, the number of turns in the primary coil is greater than the number of turns in the secondary coil. So the potential at any winding is proportional to number of turns. This is EMF. This is EMF. So EMF is directly proportional to the number of turns. If the number of turns at the secondary coil is higher, the induced EMF at the secondary coil will be high. It means that transformer is used to increase the voltage at the output. Alright?
Okay.
Okay. So I should write like this. If we want to increase or decrease so due the EMF, you just have to increase decrease the number of turns of that respective bind. Okay,
Okay.
done. Do you get it?
Okay.
No. Pira, is it possible that the input is greater than output? Sorry, the output is greater than input. Is it possible?
No.
No. Very good. The answer is no. So how do we increase the potential? Actually, Pira, when we increase the potential, we decrease the current. When we increase the potential difference decrease the current, decrease the current in that winding, in that winding. Tuba, okay,
Okay.
done. Done. So now, now let's talk about this one. Now let's see. Two coils are wound on the same core. One will generate a field in the core which induces a current in the secondary coil. This one. This is V1, source of alternating current. This is input part. And this will be now let's talk about this one. So when the switch is closed, means this circuit is complete. The potential difference across R is, what will be the potential difference? What will be the potential difference at this one? First of all, and they gave us the condition as well, that number of turns in the secondary coil is greater than the number of turns in the primary coil. So then we'll see that, first of all, this coil and this resistor are connected in series or in parallel.
Parallel.
Very good. They are connected in parallel because both the ends of the resistor are connected with the both ends of the coil. So it means that they are connected in parallel. And in parallel combination, the potential is same or different?
Same.
Very good. So they are connected in parallel. So the potential difference That's very good. Wait, Hira. Wait.
못 만나서 못 나가는 거지. 시작이 안. 못 헤어져서 못 나간다고? 에이, 그래서 못 나가는 게 아니지. 못 만나서 못 나가는 거지. 시작이 안. 못 헤어져서 못 나간다고? 뭐? 그런 거 안 봅니다. 남의 연애사가 그렇게 궁금한가? 난 모르겠는데. 심지어 헤어졌다 다시 만나는 거잖아요. 그걸 왜 보는 건지 모르겠어, 솔직히. 에이, 그래서 못 나가는 게 아니지. 못 만나서 못 나가는 거지. 시작이 안. 못 헤어져서 못 나간다고? 에이, 그래서 못 나가는 게 아니지. 못 만나서 못 나가는 거지. 시작이 안. I really like your dimple. 풀었었잖아요. 근데 이제 밥 뭐 먹었어? 아까 전에는 그거 먹었어요. 샤브샤브. 아침으로 카레 먹고.
앨범을 발매할 때쯤 되면은 불락한
머리 귀 뒤로 넘겨달라고. 귀 뒤로? 여기 비 약간.
I'm not sure is it allowed to say or not, but when I was training, I live in the homestay family house.
잠시만. 서울?
는 항상 할 게 있어.
다가 다가
Yes, Hira.
Yes.
Okay. So if they are connected in parallel, so the potential difference will be seen. Now, but tell me, if the n is greater, n2 is greater than n1, then the potential, what will be the answer? 1, 2, 3, 4, 5. What will be the answer?
Would it be 2?
Okay, let's find out. So for suppose, if this is V, then this will be V prime. Alright?
Okay.
Now, and this is V prime as well. Now let's talk about this. V prime over V is equals to N2 over N1. Okay?
Okay.
We need to find this V prime. This V moves to the right side of the equation and it multiplies with N2. Then V prime will be equal to V times N2 over N1. So this will be the answer. So the correct answer will be beta 1.
1.
Okay? Now tell me about this one, Beta. The primary coil of a transformer is connected to a battery, a resistor, and a switch. The secondary coil is connected to an ammeter. When the switch is closed, the ammeter shows zero current, a non-zero current for a short instant, a steady current. Tell me now.
Maybe
Look at the diagram very carefully, Vera, because the answer lies in the diagram. Yes, Bill. What do you have?
maybe zero current.
No. Part 2. A non-zero current for a short instant. Why? Let's find out. Vera, first of all, this is the DC source. This is a DC source, right?
Right.
So there is no current change continuously, no voltage, no current change continuously. Now, when the switch is closed, Vera, the potential at V1 and V2 is C. That is 0, 0, right?
Right.
If we suddenly close the switch, then what will happen? V1 is increasing continuously, right?
Right.
So due to the change in potential, or you can say due to the change in current, the magnetic field changes because the current initially is 0 and after that switch closes, the current increases. When the current is increasing, the potential, the magnetic field increases as well. Now, here is the change in magnetic field occur. So when the change in magnetic field is observed, according to the Faraday's law of electromagnetic induction, there has to be some current, or you can say there has to be some induced current produced in the secondary coil. Induced current is produced in the secondary coil. Alright?
Okay.
But after that, for suppose, if I close the switch, the value of current, it goes up from 0 to, for suppose, 5 ampere. Okay, 5 ampere. But this is a DC source. This DC source provides steady current, a constant current. So after reaching 5 ampere, is there any change observed in the current? Is there any change in current is observed after 5 ampere is achieved?
No.
No. Why? Because this is a DC source. DC source provides constant current. So if there is no change in current, is there any chance that magnetic field changes?
No.
No. If the magnetic field won't be changed, is the induced current produced in the secondary coil?
No.
So it means that the value of current in the secondary coil is non-zero current for a short instant, and after that the current will be 0. Simple. Got it?
Okay.
Okay. Now let's talk about the resonance. Do you know what resonance is?
Is it like the sound that is.
Very good. Resonance means matching. Resonance means matching. Matching of anything is called resonance. Now, we know that when uh, every atom or every molecule or every particle of the matter is in a motion state. The solids atom are vibrating at their mean position while the particles of fluids are moving, freely moving. So everything is in is in motion. So for suppose and if everything is in motion, it will radiate a certain amount of frequency. Radiate with a certain amount of frequency. And that frequency, if you match that frequency, for suppose the particle is vibrating at their mean position at this point, and its frequency is 50 hertz for suppose. Now, Pira, if I provide a wave of 50 hertz, now there is a matching of this wave and this particle's motion, then what will happen? There is a interference pattern will occur, and due to the matching of the same frequencies, the vibrations of the atom will be huge. The vibration of the atom will be
Huge.
huge due to the constructive interference of the vibration of the atom in the wave. So that's why glass usually breaks when when a loud sound is sounding in the environment, because everything everything has its own specific frequency. If you match that frequency, that particular particle, that particular object will be crushed. Alright?
Okay.
Now let's talk about the RLC circuit. We'll observe the frequency change in the RLC circuit. R means Pira. R means resistor. R means resistor. L means inductor. And C means capacitor. So now we are dealing such a circuit in which three components, the basic component of electronics will be considered. First one is resistor, second one is inductor, the third one is capacitor. Okay?
Okay.
Now Kira, every component every component resists the current flow This resistor has a resistance. It opposes the flow of current. Every component, each and every component shows some resistance in the flow of current. In the flow of current, the resistance R or opposition is called resistance. The inductor resistance is XL, and this is what we call inductors or inductors reactance. Inductors reactance. Okay.
Okay.
Now here is XC. XC is capacitive reactance. Capacitive reactance. This is inductive reactance. And Xc is inductive capacitive reactance. Actually, the reactances are the resistances. What is reactances, Peter?
Resistance.
They are the opposition in the path of current. Okay?
Okay.
Now, what about the resistance, or you can say the opposition of current of this whole circuit? Because resistor has the opposition resistance, inductor has the opposition inductive reactance, and the capacitor is having its resistance or opposition, and that is called capacitive reactance. So what about the overall resistance of the circuit? The overall resistance, or you can say opposition of the circuit is called impedance. It's called impedance. When we have any resistor, any component other than resistor, the circuit's total resistance or opposition is called impedance. Alright?
Okay.
Okay. So Vera, what will be the formula of impedance? Impedance represents by Z. Now, what will be the formula, Vera? Z is equals to R plus XL plus XC. Now let's see the resistance of the inductor and the resistance of the capacitor. Do you know, Peter, what is omega here? What omega is here? Omega means angular resistance, angular frequency, angular frequency. So, Peter, this is angular frequency. Now, if we talk about if we decrease the frequency of the circuit, because R is R or you can say the R does not depend upon the frequency of the circuit or the AC signal, because here is the AC source is fixed. So if we change the frequency, or suppose if we increase the frequency, the resistance of this, the frequency of if we increase the frequency, the resistance of the inductor will be increased and the capacitive reactance will be decreased, because the omega in the capacitive reactance is in denominator and in the inductive reactance the omega is the product, or you can say is in the numerator. So when we increase the frequency, this resistance will be increased and this resistance will be decreased. Okay?
Okay.
Now there has to be some frequency at which both the resistances will be seen. There has to be some frequency at which the value of these both capacitor will be increased. Actually, that frequency is called the resonant frequency. That frequency is called a resonant frequency. This is the resonant frequency. Resonant frequency means matching of frequency. Actually, when there has to be some frequency at which the value of Xc and Xl will be equal. Okay? Okay. And resonant frequency is that frequency at which the Xc and Xl will be equal, or you can say, or mostly they are zero. Mostly they are zero. Now, if you see this this is the resonant frequency. What is this? This is the resonance frequency. This is the resonant frequency. Resonant frequency represented by Fr, and at resonant frequency, these two will be equal to 0. Right?
Right.
It means that the resistance in the circuit will be minimized at this frequency, this resonant frequency, right?
Right.
And at this frequency, if the resistance will be minimum, the current will be increased. Let's see this. At resonant frequency, the current spike will be huge. Why? Because the resistance in the circuit is minimized due to the resonant frequency, due to the done.
Okay.
So here they say that the lower a circuit's resistance, how can we lower a resistance by providing a resonant frequency to the circuit. Okay? The lower a circuit's resistance, the higher and sharper is the resonance peak. See this? The 200 ohms peak is much sharper than 2000 ohm peak. Done?
So,
Yes.
what if we match the frequency to the circuit's resistance? Would it not work then?
Sorry, please come again.
So if we match the resonance frequency to the circuit's resistance, and if it was not lower?
Actually, Vera, when you provide a resonant frequency to this circuit, the two components resistance will be cancelled out. Okay?
Okay.
They will be cancelled out. If the two resistances will be cancelled, the only resistance which doesn't depend upon the frequency is R. So automatically we have reduced the resistance overall the circuit. So the current spike will be huge, obviously.
Okay.
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 So this is the RLC circuit, and this is the phenomena of resonance. Just read it, and then we'll talk about the numerical
Okay.
which I gave you as a homework. Have you done it?
Which numerical?
Wait, I'll show you. Just wait. This one, this slide setup first.
Okay.
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 Here are this numeric.
Mm.
Try to solve it, Vera. I'm waiting.
Okay. Rectangular loop with a resistance R equals 5 ohms of width moves into the large region of magnetic field as shown the velocity. And partly, what is the current?
Vera, how many chapters are in the midterm examination?
About 5. I'm pretty sure 5.
And what chapters?
I'll send it to you at the end just to make sure about the chapters. Okay.